We are now ready to consider Gauss's law. An important aspect of Gauss's law is the notion of a surface. A surface is an idea from mathematics, and here are a few pictures of some different surfaces. Looking at these pictures, we see that surfaces can be simple in their shape. Surfaces could be spheres or donuts or disks, but surfaces could also be more arbitrary in their shape, such as the surface of an amoeba. Surfaces themselves could also be categorized as being open or closed. In this picture, we see three examples of some closed surfaces and three examples of some open surfaces. So let's look carefully at these open and closed surfaces. And I'm going to say at this point, pause the video and see if you could come up with a rule that will allow us to distinguish between a closed surface versus an open surface. One way we could differentiate between a closed surface versus an open surface is we could say a closed surface contains a well-defined notion of inside versus outside. The surface itself is the boundary between the inside and the outside. An open surface is not going to have any such distinction. Another way of thinking about this idea is we could say a closed surface will encompass some non-zero volume. Another way we could possibly differentiate between a closed surface versus an open surface is we could say an open surface contains an edge. A closed surface does not have any such edge. If we are walking along a sphere, we will always be able to walk along the sphere forever. We'll never encounter an edge. The same is true for a donut. Even if we're walking along the surface of this cube, we walk along the top face of the cube, and then we come to the corner of the face, but then we just are turned and walking down the side face. On the other hand, if we are walking along this hemisphere, we will eventually encounter the edge of it. The concept of a closed surface is going to be very necessary for understanding Gauss's law. To introduce Gauss's law, I first want to give an analogy. Let us suppose that we have a glass jar that is just floating somewhere between the stars. For the purpose of this analogy, I do not want the glass jar to actually be in physical contact with anything. I don't want it sitting on a table. So that's why I chose to place the jar somewhere in the middle of space. Let us also assume that this jar is completely transparent everywhere over its surface. So the sides of the jar and the lid and the base are all made of glass. I am not going to tell you anything about what may or may not be inside the jar, but I will also tell you that every second 10 to the 8 particles of light will pass from outside the jar through the glass to the inside of the jar, and simultaneously every second there will be 10 to the 12 particles of light that exit the jar. In other words, every second there will be 10 to the 12 photons that begin inside the jar, pass through the glass, and move on to outside the jar. So we have a scenario that looks something like this. Now I'm going to ask you a few questions about what may or may not be inside the jar. So after each question, pause the video, think about it, and then continue. So the first question I'm going to ask: can we come to any conclusion about whether or not there is a source of light inside the jar? The answer to that is yes, we can. We could imagine that because there are more particles of light exiting the jar than entering the jar, there must be a source of light. There must be something that is creating light inside the jar. Then that light will be streaming away from the source and passing through the glass walls of the jar eventually, so there must be a source of light inside the jar. As a second question, can we make a statement about the brightness of that light? In other words, how many photons per second is that light giving off? Again, we can make a statement about how bright the light is. We can take the difference between the number of photons that are exiting every second and the number of photons that are entering every second, And the difference between these two numbers will be the excess photons that are created each second inside the jar and then stream away from the light. As a third question, is it possible to discern whether there is one single bright light inside the jar or multiple dim lights inside the jar? The answer to that question is no. We cannot tell the difference between these two scenarios only given the information that we have. We know how much light total is created each second inside the jar, but we can't tell between these two scenarios. As a fourth question, is it possible to know the location of these one or more lights inside the jar? Could the lights be near the center, near a wall of the jar, something else? The answer to this question again is no. We cannot know the location of the lights. We could conclude that there must be some source of light inside the jar. We could conclude how bright the light is overall because we know how many photons each second the light creates, but we cannot know anything about the location of these lights. Let us now consider the scenario where every second we have 10 to the 10 photons entering the jar from the outside, and simultaneously every second we have 10 to the 10 photons exiting the jar. So we have a picture that looks something like this. Given this scenario, can you make any statement about whether or not there is a source of light inside the jar? There is not a source of light inside the jar. You could imagine that this jar could be surrounded by stars, and light from those stars that hits the surface of the jar will enter the jar, but that light will just pass through the jar, eventually reaching the opposite wall of the jar and exiting. So overall, there is no net amount of light entering or exiting the jar. If there were a source of light inside the jar, you would expect that that source of light will create photons. Those photons will stream away from the light source, and overall there would be more light exiting the jar than entering the jar, like what we saw in the previous example. Let's now consider this possibility. Let's say every second there are 10 to the 10 photons entering the jar, but only 10 to the 6 photons exiting the jar. So now we have a scenario where more light is entering the jar than exiting the jar. Can you think of any possible scenario where this might be true? In order to realize this scenario, you would need to devise some way to destroy or remove some of the light that enters the jar. One way you could possibly do that is to imagine that there is a black hole inside the jar. In this case, there will be some number of photons that are entering the jar from the outside. Some of those photons will hit the black hole and be effectively destroyed, while other photons will miss the black hole and be able to reach the surface of the jar and exit. In that case, it will be possible to have more light entering the jar than exiting the jar. As a final analogy, let's suppose again that every second we have the same number of photons entering the jar as we have exiting the jar, but we will now assume that there is a source of light inside the jar. Is there any possible scenario where this could be realized? In order to have the same amount of light entering the jar as we have exiting the jar and have a source of light inside the jar, we would also need to have a black hole inside the jar as well. In this case, for every particle of light that the light source creates, we would need to have the black hole destroy a particle of light. Then we would be able to achieve this balance where the total amount of light entering the jar is equal to the total amount of light exiting the jar every second. In these analogies, the source of light could be thought of as a positive electric charge. The black hole could be thought of as a negative electric charge. The glass jar itself could be thought of as a closed surface, which is sometimes referred to in these scenarios as a closed Gaussian surface. And the photons, the particles of light, could be likened to the electric field. Now, I also just have the asterisk here because in this analogy, the photons are moving objects. When we work with electric fields, there is nothing that is actually moving, But we still visualize electric fields as arrows filling space. So we could imagine an arrow pointing into a jar as opposed to pointing out of a jar. Here we have a picture of a closed surface and the electric field lines that pass through that closed surface. The electric field is a vector field quantity. That means the electric field will exist at every location in space. But for this picture, we chose to only show the electric field lines that pass through the surface. We also chose to draw the surface as an arbitrary shape, and the charge that creates this electric field was not shown. So, given this information provided in the picture, can you come to any conclusion about any charge that may or may not be inside this closed surface? We could conclude that there will be some amount of charge inside this closed surface, and that charge will be negative. How do we come to that conclusion? Well, notice that there are more electric field lines entering the surface than exiting it. Remember from a previous video that the electric field created by a negative charge will point towards the negative charge. I look at this picture and I see there are 8 electric field lines passing from the outside to the inside of the surface, and there are 0 electric field lines pointing from the inside to the outside. So I expect there is going to be a sink of electric field lines. In other words, there will be a negative charge. Also, if you think back to the previous analogy, we said if you place a black hole inside a glass jar, it is possible to have the scenario where you have more photons entering the jar than exiting the jar. Also, if we were to be given some type of conversion for how many coulombs of charge create how many lines of electric field, we would even be able to then say how much charge exactly is inside this closed surface. For example, if I said 1 coulomb of charge creates 4 electric field lines, then I could count and I could say there are 8 electric field lines, so overall there will be -2 coulombs of charge within this closed surface. If I were to draw the charge and all the electric field lines in this picture, I would have something that looks like this. Here is another arbitrarily shaped closed surface, and again we are only shown the electric field lines that pass through that surface. Can we make any statement about whether or not there is any electric charge inside this closed surface? In this case, there is no net charge inside this closed surface. How do we come to this conclusion? Well, notice that for every electric field line that enters the surface, there is also an electric field line that exits the surface. Let's think about what we would expect to see if there were a net positive charge inside this closed surface. We learned that positive charges create electric fields that point away from the charge, and so if there were a positive charge inside this surface, there would be an electric field surrounding the charge, pointing away from it at every location. And at the location of this surface, the electric field from that charge would be pointing outward through the surface. But that's not what we see. We see equal number of electric field lines entering the surface as exiting the surface. So we could conclude overall there is going to be no net charge inside the surface. Now, how should we think about the electric flux through the surface? A natural way to think about the electric flux through a closed surface is to imagine that an inward pointing electric field line will cancel with an outward pointing electric field line. In this particular picture, we see there are 7 inward pointing electric field lines and 7 outward pointing electric field lines. So we could say that the total flux through this entire surface is going to be 0. In the previous example, we have more inward pointing electric field lines than outward pointing electric field lines. So in this example, there will be a non-zero amount of electric flux passing through the surface. If we want to deal with electric flux mathematically, we need some convention for allowing an inward pointing electric field line to cancel with an outward pointing electric field line. So we will adopt the convention that an inward pointing electric field line will contribute a negative amount of electric flux, and an outward pointing electric field line will contribute a positive amount of electric flux. And notice from the picture shown here, the total flux through this surface is going to be negative because the electric field lines are pointing inward, and we have a negative charge that is creating this electric field. If we were to draw all the electric field lines in this picture, we would get a picture that looks something like this. We are now ready to introduce Gauss's law. Gauss's law is a relationship that connects the total amount of charge inside a closed surface to the total electric flux through that surface. Looking at Gauss's law, we see that mathematically Gauss's law is a very simple relationship. The total flux through the surface is equal to the net charge inside the surface, which we call Q enclosed. There also is this factor of 1 over epsilon naught on the right-hand side of Gauss's law, but remember that epsilon naught is just a constant of nature. What I really want you to focus on is the net charge inside a surface automatically sets the total amount of electric flux through that surface. If you are working on a homework or an exam problem, epsilon naught would just be a number that you look up in a table, and you could always multiply or divide by a number. To finish off this discussion of Gauss's law, I want to make a few comments. First of all, notice that the right-hand side of Gauss's law that contains Q enclosed does not make any statement about how many charges are inside my closed surface or how those charges are distributed. Gauss's law only cares about the net charge inside the surface. So if I have a total charge of +4 within the surface, I might have a single +4 charge, I might have 4 +1 charges, I might have 8 +1 charges and 4 -1 charges. In all of those scenarios, I have the same net charge inside my surface, so I will be guaranteed to have the same total electric flux through the entire surface. Also, it does not matter if those charges are near the center of my surface or out towards the edges, I will still have the same total electric flux over the entire surface. Also, Gauss's law does not care about the size or shape of my closed surface, which is often referred to as a Gaussian surface. As long as the surface is closed, Gauss's law will be valid. It doesn't matter if I have a large surface or a small surface, if it's a simple shape or a more amorphous blob. As long as my surface is closed, I can apply Gauss's law. What we're going to see in the next video is, in some scenarios, if we have a high degree of symmetry in the problem, then it will be possible to apply Gauss's law to know the flux through open surfaces as well.